Assalamu alaikum. I welcome you in my NPTEL UGC Chalk Talk classes. And as already communicated to you, I am planning to start NEET JEE course for students aspiring to qualify NEET JEE and students who presently are in 11th and 12th but who dream to qualify JEE NEET. And today I will discuss with you one important topic from transition elements which is applicative in itself, and topic is catalytic properties of transition elements. Transition elements and their compounds are used as catalysts to increase the rates of reaction in industries and in laboratories. Transition elements और इनके compounds industries या laboratories में इस्तेमाल किए जाते हैं as catalysts to increase rates of reaction, to increase rate of conversion of reactants into products. अब question arises, how transition elements and their compounds are able to increase the rates of reaction, how they are able to act as catalysts. And let me answer you this. How? Before this, let me give you some instances. Iron is used as catalyst in manufacture of ammonia by Haber's process. You all have studied, 12th class students might have studied in 11th class in chapter equilibrium. Iron is used as catalyst in Haber's process for manufacture of ammonia, and it is one of the most important industrial process. Similarly, nickel is used as catalyst in hydrogenation of ethene to ethene. Similarly, Ziegler-Natta catalyst, whose composition is triethyl aluminum and titanium tetrachloride, is used as catalyst in polymerization of ethene to polyethene. And this in itself you will study in chapter polymer chemistry. And here transition element involved is titanium in +4 oxidation state. Similarly, cobalt is used in synthesis of gasoline, petrol. Similarly, one more example I can give, vanadium pentoxide is used as catalyst in manufacture of sulfuric acid. Here it catalyzes one of the important steps which involves conversion of sulfur dioxide into sulfur trioxide. So from all these examples which I quoted, you got idea, you got clue, or you got evidence that transition elements or their compounds are used as catalysts. Now let me come to how. In order to answer this how, I need you to have some information of chemical kinetics, in which we study rates of reaction, factors affecting rates of reaction, and mechanism of reactions. And in kinetics itself, we have studied, two kinetic, you are familiar with two kinetic equations. R is equal to K concentration of reactant within square brackets. Suppose we have a reaction, reactant gives products. And for this reaction, as per kinetics, its rate has direct dependence on rate constant, and its rate has direct dependence on concentration of reactants. Such that if you will start the reaction with greater initial concentration of reactants, rate of reaction will be greater. If you will start reaction with less concentration of reactants, rate of reaction will be less. And consider there are two reactions, and in both these reactions you start with same initial concentration of reactant. Then dependence of rate on concentration of reactant goes. Rate in these two reactions will now only depend on rate constant, such that one having greater rate constant will have greater rate of reaction. So this physical significance of this equation is that it conveys us that rate of reaction has direct dependence on K, and rate of reaction has direct dependence on concentration of reactants. Direct dependence. Second equation is this: rate constant is equal to A e raised power minus EA divided by RT. And here in this equation, rate constant in itself has dependence on variable parameter activation energy and variable parameter temperature. I can write this equation as this to know its physical significance. K is equal to A divided by e raised power plus EA by RT. Here what I did, I took this exponential factor from numerator to denominator such that its power got changed, its power got changed in sign, and it is not positive. Power is not positive. Prior it was negative. And from this mathematical equation we get to know that if activation energy is less, this denominator portion, exponential portion in the denominator will be less, and rate constant will be less, and as per this equation, rate of reaction will be less. So here we get to know that rate of reaction has direct dependence, has inverse dependence. Let me cross check it. Activation energy less. This is activation energy less, denominator is less. K will be more. I am correcting here. Rate constant, rate of reaction will also be more. Now you see, less activation energy, more rate of reaction. So rate of reaction has inverse dependence on activation energy. The reaction whose activation energy is less, its rate will be more. The reaction whose activation energy requirement is more, its rate will be less. So I conclude that rate of reaction has inverse dependence on activation energy. If activation energy is greater, rate of reaction will be less. One more idea I will take from chemical kinetics, that is role of catalyst, and same role will be played by transition element or its compound. Role of catalyst. Catalyst takes reaction via an alternate path. Usually this path is multi-step path involving number of steps, and special feature in this multi-step path is, let me first write, catalyst takes reaction via multi-step path, alternate path, and in this alternate path activation energy is less, such that rate, on this basis I can conclude that rate of reaction will be more. This is role played by any catalyst, that it provides alternate path to the reaction, which is usually a multi-step path involving more than one step, and here in this path activation energy is lowered such that rate gets enhanced, improved. Same is done by transition element or its compound when it plays role of a catalyst. So transition element, let me finish this question. How transition element and their compounds are able to act as catalysts? We will answer it like this, that transition element and their compounds are able to provide alternate path, multi-step path to the reaction requiring low activation energy, so improving the rate of reaction. Now second question which I need to answer is why transition elements and their compounds are able to act as catalysts. In order to answer this question, I will exploit I can exploit two or more than two explanations. Let me give explanation first. Due to presence of unpaired electrons, in D subshell, this you get to know from electronic configuration. If a student is able to write the electronic configuration of D block element, then he or she knows that they got their last electron. They have their last electron in D subshell of penultimate shell, and only those elements, D block elements or transition elements, which have partly filled D subshell, and having this partly filled D subshell means they have unpaired electrons in D subshell, and it is due to presence of, it is a specialty of these unpaired electrons present in D subshell, which gives transition element and catalyst role, transition element and its compound role as a catalyst. So explanation is due to presence of unpaired electrons in D subshell. Now how it works, how it goes, let me show. I will take a reaction, that is hydrogenation of ethene gas to form ethane. This is addition. This is basically addition reaction, and addition reaction, and here addition of hydrogen occurs across carbon-carbon double bond, during which one double bond to carbon gets one hydrogen, another double bond to carbon also gets one hydrogen, and after addition double bond to carbon changes into single bond to carbon in order to have tetravalency of carbon satisfied, that you all know. This is gas, this is also gas, and this is also gas. So I mean to say it is homogeneous gaseous reaction, and if it is carried in absence of catalyst, it takes long time for a product to be formed. So we as chemists we use here nickel as catalyst. Nickel is a transition element in first transition series, which is a member of first transition series, and as catalyst how it works, how it acts, let me explain. Nickel has atomic number 28, and if you write its electronic configuration, it will be 4:3d8, and when you will distribute these 8 electrons in its d subshell, you will find that there are 2 unpaired electrons, and due to these 2 unpaired electrons it will act as a catalyst. Let me further explain it. Consider this board as it is nickel and it is its surface. It is its surface. Now nickel atoms present at the surface have presence of 2 unpaired electrons, and due to these 2 unpaired electrons, these surface atoms of nickel are highly reactive. So what they will do? I imagine this as nickel. This board you imagine as if it is nickel, and this is its surface, and on its surface there are nickel atoms with 2 unpaired electrons, and because of presence of these 2 unpaired electrons which have tendency to get paired, these surface atoms, these nickel atoms present at surface are highly reactive. So what will they do? Imagine here is ethene gas. For example, let me try like this. Imagine this is ethene gas and this is hydrogen gas. So what happens? Because it is highly reactive surface, it will attract these reactants towards itself. So first setup here occurring is that reactants will diffuse towards the surface of catalyst because it is attractive surface. Next, these reactants will get adsorbed on the surface. These reactants will get adsorbed on the surface, and here covalent bond formation will occur between surface and the reactants. New covalent bonds are formed, but between what and what? Between surface and between reactants. And further, within reactants, if you imagine it is ethene gas and it is hydrogen gas, within reactants there is breaking of bonds, and this breaking of bonds within reactants, which is associated with adsorption, it results in lowering of activation energy, hence increasing the rate of reaction. Not only this, concentration of reactants on this, as a result of adsorption, with time concentration of reactants on the surface increases, so will increase the rate of reaction, and it will also provide effective orientation. After adsorption, these reactants will have effective orientation in order to form products as is demanded by collision theory, which you have studied in chemical kinetics. Let me track all these steps. First, diffusion of reactants towards surface, then adsorption of reactants at the surface. It is important step because here new bonds are formed between surface and reactants, and old bonds within reactants are broken, resulting in lowering of activation energy. Third step is, and it also increases concentration of reactants on the surface and provides effective orientation. Third is chemical reaction at the surface, and during this reactants get converted into product. And next step is desorption of products from the surface. Now bonds between product and surface will break, they will undergo cleavage, and last step will be diffusion of products away from the surface, and that product here will be ethane gas. So what are the steps? There are 5 steps in this alternate path, multi-step path: diffusion of reactants towards surface, adsorption of reactants at surface, chemical reaction at surface, desorption of products from surface, diffusion of products away from the surface. And in this multi-step path, so many so many features are added, like activation energy is lowered, like concentration is increased, like effective orientation is provided, hence increasing the rate of reaction. So justifying my point that they do provide an alternate path to the reaction, hence increasing their rate. Now second explanation I can give, that is presence of explanation second. Presence of it is first explanation. Second is tendency to show variable oxidation state. Transition elements have their outermost electrons in valence shell as well as penultimate shell. So they have valence shell incomplete, penultimate shell incomplete. So valence shell unstable, penultimate shell unstable. So what they do in bonding, in addition to 2 electrons from valence shell, they can involve different number of electrons from penultimate d subshell. Hence they can show variable oxidation state, more than one oxidation state. Like iron, you have iron. Iron shows 2 oxidation states. One is +2 and one is +3, named as ferric ion and ferrous ion. In higher oxidation state is named as ferric, and in lower it is named as ferrous. So you got to know that they have property that they show variable oxidation state, and this property is helping them to act as catalyst. How? Let me explain. I will give an example. Very important reaction. Iodide ion reacts with thiosulfate ion to form iodine molecule and sulfate ion. Iodine in this reaction undergoes oxidation. Iodide in this reaction undergoes oxidation, so it will act as a reducing agent. Thiosulfate ion in this reaction is reduced, hence it will act as oxidizing agent. So it is a reaction basically carried between reducing agent and oxidizing agent. It is an oxidation reduction reaction, redox reaction. I will not go into details by writing oxidation number of atoms in reactant size and product size, so that you will follow where is increase in oxidation state, where is decrease in oxidation state, that you already know. Just additional information regarding this reaction is that here iodide acts as